So again, to select 1 volt, we need to make sure that pin 8 is connected to 5 volts, and pin 9 is connected to ground, and pin 10 is connected to ground. This is what we have here. So pin 8, as you can see here, pin 8 is connected to 5 volts. It's connected to the red rail, and pin 9 and 10 are connected to ground. They're connected to the blue. So on the voltage across the resistor is 0.989 volts. It's very close to 1. So we need to indicate this here in our table. 0. Okay. 0.989. Okay. 0.989. Okay. Then also we can calculate the current, and of course the current will be voltage over resistance, because the resistance is fixed. So this would be 0.989 divided by 470, and that will give us our current. And again, we're going to populate it here in a little while. So let's go ahead and get the voltage for 2. Now for 2, we need pin 8 to be 0, pin 9 to be 1. So let's go ahead and change these ones. So pin 8 needs to go back on 0, and pin 9 is going to be on 1. Okay? And so now we can see our output voltage is 1.955, which is close to 2. And of course, we have a small feature here. You can see also that the light is blinking 2 times. So it blinks twice and it has a break. Okay? So now we can write that voltage here, which will be 1.955. Of course, this is volts. Volts. Okay, let's go ahead and do 3 for free. We need pin 8 to be 1, pin 9 to be 1, and pin 10 to be 0. So let me go ahead and just move pin 9 to be, pin 8 now to be 1 as well. So pin 8 is 1, pin 9 is 1. And again, we can see that our voltage is 2.91920, which is close to 3. Not exactly 3, but close to 3. So we're going to write it here. 2.919 volts. Okay, then we move to 4. For 4, we need pin 10 to be 1, pin 9 to be 0, pin 8 to be 0. So let me go ahead and move pin 10 to be 1. And also I'm going to move pin 8 and 9 back to 0. Alright, so now we have 3.888 volts. So it's not exactly 4 volts. 3.888 volts. And then the last one for 10, we need now pin 10 to be 1, pin 9 to be 0, and pin 8 to be 1. So I'm just going to move pin 8 from 0 to 1. And of course, we can see that our light is blinking 5 times now. 1, 2, 3, 4, 5. Alright, so the voltage we have is 4.93 volts. And again, we are measuring the voltage because most times the voltage is not exact. So we need to get the exact voltage so we can be more accurate in our current calculations. Now we can go ahead and calculate the current for each of these. So in this case, it's going to be 0.989 divided by 470, and that gives us 0.0210. 0.00210, which is the same, and we can write this in milliamps. So this would be 2.1 milliamps. So we just write 2.1 because it already says that the current is in milliamps. So it would be 2.1. 2.1. Likewise, we can calculate the current. Okay, this one should go right here. 0.00. Likewise, we can calculate the current here, 1.955 divided by 470, which is the, and we should not use 470, but we should actually use the measured resistance. So let me go back and do the calculation. So the measured resistance for hair is 460. So let me cross this one out and remeasure it. So in this case here, 0.989 divided by 460 would give us 2.15 milliamps. Okay, in this case here, 1.955 divided by 460 will give us 4. So this will give us 4.25 milliamps. Okay, this case here, 2.919 divided by 460 will give us 6.345 milliamps. Okay, 6.34 milliamps. Also, now we can also do this one for 4 volts, 3.88. 3.888 divided by 460 will give us 8.45 milliamps. Okay, and lastly, 4.93 volts divided by 460 will give us 10.7 2 milliamps. Okay, so now we have the currents. Okay, we have the voltages. Now we can use these values to plot our graph, which is the last step in the experiment. So we can see that the relationship, we can see that when we plot current versus voltage for a fixed resistor, the response is a straight line. And we'll go ahead and get a quick sketch of the graph quickly. So here I have a graph and we're going to plot some values. Okay, so I can go ahead and make a plot quickly. Okay, so I'll start right here. So this one will be current in milliamps. And this one will be voltage in volts. Okay, and now I can plot the values that we just got here. So for 0, it's going to be 0. So the current is 0. Then we can go ahead and put the voltages here. Then we have point. So if we take this one to be, this would be, so we only need 5 volts. If we use each one for 1, 2, 3, 4, 5. So this one could be 1 volt. Then we could do 1, 2, 3, 4, 5. This one will be 2 volts. Then we can do 1, 2, 3, 4, 5. This will be 3 volts. 1, 2, 3, 4, 5. This one will be 3 volts, 4 volts. And 1, 2, 3, 4, 5. This will be 5 volts, right? Likewise, we need to go up to about 10 point or 11 or say 12 milliamps. So we can divide this into 12. If we take 4 here, 1, 2, 3, 4, 5, 6. So we can go ahead and take 3. If we take 3, 1, 2, 3, 4, 5, 6. Right? Yeah, we can go ahead and take 3. I'll take 2, right? So this would be 1 milliamp, this would be 2 milliamps, 3 milliamps, 4 milliamps, 5 milliamps, 6 milliamps, 7 milliamps, 8 milliamps, 9 milliamps, 10 milliamps, and then 12 milliamps, right? So the first one, for 0, we have the 0.0 here. So now we move to 0.98 volts. So 0.98 volts will fall somewhere around here, alright? Very close to 1. And then the current that we have is, the first current is 2.15 milliamps. So 2.15 milliamps will come somewhere here. So we can go ahead and see that the point will be somewhere there. Alright? The second point we have is 1.955 volts. So 1.955 is very close to, okay, it's very close to 2. So it will be about here. Okay, and the current that we have is 4.25. So again, this is 2, this will be 4.25, and 0.25 is almost like a quarter. So we can trace it here. So the point will be about here. Likewise, we have the second point we have is 2.91. So 2.91 is very close. So again, if this is 1 here, it means that each of these is 2, right? So 9 would be like half of this one, right? And then the current is 6.34. So again, this is 1, 2, 3, 4, 5, 6.34. So again, this is here 6.5. So 6.34 would be about here. So if we follow this here, we are almost in the center here, and we are at 6.34, which is the little here. So this is the point right there. Then we go to 4 volts, which is 3.88. So we come here. So we have 1, 2, 3.88. Now again, it's like almost halfway there, almost 3.9. And then the current for this is 8.45. So again, this is 6, 7, 8, 9, 10. Hold on. 1, 2, 3, 4, 5, 6, 7, 8. So this is 8 here. 8.45. So again, it's close to 5. So I'll just go with 5. And now the point is right here. So the center there. So this would be the point right here, 8.45. And then lastly, we have 4.93 volts. So this is 4.9 here. So we'll use that here. And then the current is 10.72. So again, this is 8.5. This is 9. This is 10. 10.72. Okay, so this is 10.72 about here. Okay. So if I take this one here, and I come to look for it, so the point is about here. Okay, so if we were to put a straight line for this point, okay, we see that we have a linear fit, and that goes to prove that the relationship between the current and the current and the voltage is directly proportional for a fixed resistor, right? And we can also get the slope of this line. So the last table in your graph, in your lab, asks you for the slope of the line. Now the slope is very easy to calculate. It's rise over run. So this final table asks you for the slope. It says what is the slope here, okay? And of course we can use our points to calculate the slope. So we have these 2 points here. The slope would be change in y over change in x, okay? Based on the table, change in y over change in x, and you report your slope right there, right? Also, we can see that we can also flip this graph around. We can have current on the x-axis, and we can have voltage on the y-axis, and we can also get the slope. And we will see that the slope, instead of the slope being resistance, it will be conductance, and we'll talk more about that as we go on. Okay, so, and how long?